Okay. So let's review where we are in this account of how we're going to coarse-grain a cellular automata not just in time but also in space. On the bottom half of this diagram is what we already know how to do. We know how to take the fine-grained state of the system at time t1 and move it forward using the standard rule that defined our cellular automata to begin with, the F rule. In fact, in order to do this diagram, what we're going to ask you to do is think about not just figuring out the value of the grid point at some point in time t equals 3, but actually a pair of grid points. And so here's, for example, how you would figure out the value of the grid point here, which we've called C1, 2 time steps in the future. Well, we know that C1 is gotten from evolving the system forward using its 3 neighbors in space and time, B1, B2, and B3. And then we know furthermore that in order to get the values of these 3 things here, we have to use the data from the previous time step, which gets a little bit larger. But in the end, this function here, how we can get the state of these 2 grid cells 3 time steps in the future, or rather 2 time steps in the future from where we began, in order to get these 2 grid squares here, all we have to do is use this function f. What we're going to do is write this long process here in a more efficient fashion. We'll write f hat, which takes in this supercell pair here, A1 and A2. We'll call that A1 hat. This supercell here, we'll call that A2 hat. And this supercell here, we'll call that A3 hat. And out the other side, that will give us the supercell 2 time steps in the future, C hat. So the structure of this here is completely defined by the original evolution rule F. If we were in the Markov chain case, we'd be done. With the Markov chains, we could construct the 2 coarse-grained Markov chain, the 2-step coarse-grained Markov chain from the 1-step fine-grained case, just by manipulating that evolution rule. The problem is, in this case here, f hat takes a different form from f. In order to solve that problem, we invent a coarse-graining in space as well, this projection operator p. And what p is going to do is map a supercell such as a hat 1, which takes on 4 possible values, and maps that to some possible set of choices, and I'll mix them up from last time, to some set of choices of a single binary variable. Our goal is to find a p such that if we do that projection, we can find a standard CA rule G that now takes in not supercells, but binary variables constructed out of those supercells, and produces an answer that agrees with the bottom pathway where we evolve forward using the f hat rule and then projected at the end. There are some trivial forms of p that will always work. So here's an obvious example. Let's say the projection operator p just blanks out the state. So whatever the input value of the supercell is, it always says that it's equal to 0. In that case, if we evolve forward on the fine-grained level, then after 2 time steps we have some complicated pattern. That complicated pattern is completely wiped out by the projection operator, and it's all zeros. Similarly, if we begin with some complicated set of initial conditions, but we do the projection operator, those initial conditions become trivial, everything is 0, and then all we have to do is pick a rule G such that it always takes zeros into zeros. And in fact, that's equivalent to the rule 0 case. So in that case, we can pick a p for any function f. We can always find a p if it has this trivial property. In that case, yes, well done, you renormalized, but you renormalized by doing a coarse-graining that's so severe that everything looks identical, which is not a lot of fun. So what we're going to do when we take a particular cellular automata, f, we're going to ask for a p that doesn't have this property. And in particular, the only thing we're going to do is put a constraint on p that says that it can't map all the variables trivially either to all zeros or all ones. Having made that one restriction, the problem now becomes interesting. It says for any particular f, can you find a non-trivial projection and an evolution rule drawn from the same set such that this diagram, again, has the commutation property. In order to find that set of projections, there's a couple different ways to do it. In the original paper by Israeli and Goldenfeld, what they did was just search over the entire binary space. In particular, for a projection P, all you have to do is check all of the 4 possible inputs to see if they work. So for example, you could pick, let's say, this one goes to 1, this one goes to 0, this one goes to 0, and this one goes to 1. Okay? In that case, the projection operator sort of like sort of an anti-parity operator. So you'd pick that P, and then you'd cycle through all of the 256 possible cellular automata to see if any of them made the diagram commute, i.e. if you did this projection and then used that particular choice, maybe that would be rule 50, could you get the diagram to commute? And if the answer is no, you cycle through all the 256 rules. Okay, try a different projection operator. Maybe you would try this one here. So you try that projection operator, and then you'd cycle again through all the 256 routes. So what Israeli and Goldenfeld did essentially was just a brute force solution to the problem of finding renormalized theories and accompanying coarse grainings.